Hey Tiange, what are you doing?
Oh, I'm just feeding my gut microbes.
What?
What you eat is not only what you eat, it's also what your microbes eat. And green banana has a lot of resistant starch, which is a type of fiber, and it can be degraded by our gut microbes. To better understand this interaction, we categorize our carbohydrates into 4 groups.
The first group is HAS, for example, simple sugar, is fully digested in the upper gastrointestinal tract. HAS is not what we call fiber. Resistant starch in green banana is where we can start to call fiber because it's partly digested in the small intestine and the rest will go to the large intestine, where gut microbes can break it down and produce short-chain fatty acid, for example, butyrate. Another type of fiber is MAC, for example, inulin. The digestion is fully dependent on the gut microbes in the large intestine, also providing short-chain fatty acids beneficial for our health. Butyrate is absorbed by the gut epithelium, providing energy and promoting blood supply to keep the tissue healthy. Indigestible carbohydrates is another type of fiber, such as cellulose, which cannot be degraded by us or by microbes.
Within these 4 carbohydrate groups, the benefits of microbial fiber interaction relies on HAC and MAC, which are commonly known as prebiotics or fiber.
But what type of fiber and how much do we need? So our first aim is to study how different proportion of different types of fiber shapes the gut microbial community.
Does it mean you only eat fiber and nothing else? No, we need other food components as well, such as protein and fat, and the total energy density is important as well. So our second aim of this study is to look at the fiber microbial interaction within the context of different protein level and energy density. And we hypothesize this protein level and energy density difference will impact our interaction as well.
So our study will answer how much fiber do I need, with the hypothesis the amount of fiber you need depends on the fiber type, what other food you're taking with, and how much you eat. To test the hypothesis, we designed 40 different diets with different fiber profile and different protein to carbohydrates ratio, and also different energy density. Here's an easy way to understand. We start from a low protein, high carb pizza with a lot of sauce and tomatoes topping with a plain pizza base. We then add different fiber into the pizza base to change the fiber components. We replace half of the pizza with cellulose to reduce the energy density so the mice eat less digestible food. If switching the toppings to pepperoni, we have high protein and low carb pizza. We add cellulose again to reduce the energy density. Due to the time limit, I will be only looking at these 8 diets. To study the effect of different fiber, we look at these groups with same protein to carbohydrates ratio, same energy density, but different fiber proportion. To study the effect of protein and the amount of food intake, we'll look at these groups with the same fiber profile, but different protein level and energy density. Each diet was given to 3 mice in 1 cage lasting for 5 days. We collected their fecal sample at day 3 and day 5 on this diet. The mice was given standard chow for 1 day before switching to the next diet. To study the gut microbes, first I need to do DNA extraction. I used homogenizer to break off the cells and release DNA. I then add the binding matrix to attach DNA. After several washing, I eluted the fecal bacteria DNA. When the primates arrived, I did qPCR on the specific 16S gene on Bacteroides and Faecalibacterium prausniziae, and also universal gene on all bacteria as a reference. I then used the delta CD value to measure the relative abundance of Bacteroides and Faecalibacterium prausniziae. If we only look at the protein to carbohydrates ratio of the diet, ignoring other factors, we found low protein, high carbohydrates diet has a higher relative abundance of Bacteroides than the high protein, low carbohydrates diet. So, in high protein diet, Bacteroides are outcompeted by other bacteria that have more advantages in utilizing protein. Let's have a closer look at the high protein diets. When protein level and energy density is high, changing MAC doesn't make a significant shift in bacteria's relative abundance. However, when energy density is reduced to half by cellulose, high MAC causes a reduction in bacteria's relative abundance. This is because when half of the food is indigestible cellulose, mice have less access to digestible nutrients, for example sucrose and resistant starch, which are the major food source for bacteriides. High MAC in diet even makes it more difficult for bacteriides to access sucrose and resistant starch, and other bacteria utilizing MAC better can outcompete bacteriides. Therefore, you not only have to feed your microbes with the right type of fiber with the right proportion, but also the other food components you're feeding with, such as protein and energy density, matter as well. For Faecalibacterium, my qPCR results showed the abundance was close to zero. Andy's normal lunch includes a small piece of honey soy chicken and a large amount of vegetables with brown rice. This is similar to our mouse with high protein and low energy density and high fiber diet, so he is starving his bacteriides. Alison is often found at desk eating chocolate, so she had a low protein, high carbohydrates diet. Therefore, she has a high abundance of bacteriides. But how is this associated with health outcomes? To answer this, we need to further look at the interaction of the diet and other bacterial species, and also the mice metabolism, physiology, and immune function with a long-term diet.
How are you today?
Doctor, I'm still not feeling very good.
Let's have a look at your fecal sample.
Here you go.
Thank you. So first, we do a DNA extraction on the fecal sample. That's the DNA, and now we do a qPCR. So this is your qPCR results. The result showed you have really low level of bacteriides in your gut, which means you need more fiber in your diet. Here you are. Good luck.
Thank you, doctor.
Cheers.